Okay. Now, if you have, I give you a brief summary of the electric field here. Now, if you have point charges, you're supposed to use the inverse square law, right? F equals to Q1, Q2 over 4 pi E naught R squared, right? And the electric PE becomes this formula if it's for point charges. Now, if U will depend on the value of Q1 or Q2 lah, right? So if Q1 is negative, right, to put in Q1 as negative, right, or Q2 as negative, you have to put in the negative sign. The negative sign does not tell you that it's a scalar, it's a vector, right? Because Q1, if it's negative, you put in the negative sign itself, right? It's already a scalar. Let's say, for example, minus 5 coulomb, right? It's a scalar already there, because it's a size. Okay, then you have to know this, okay? Your definition for electric field, they always ask, okay? And the work done, right? Must know to bring potential is the work done per unit charge, right? So these are formulas that you have to know. And these two formulas are actually E equals to F over Q, V equals to W over Q. It does not only apply to point charges, it applies to everything, right? All the electric field stuff, right? Now, this relationship also applies to all situations, okay? Regardless whether it's a point charge or it's a parallel plate, right? Sometimes they'll ask you, why is there a negative sign, right, in this equation, E equals to minus dV dr. The minus sign arises because in the direction of the increasing potential, the electric field points the opposite direction. Because electric field always point from high to low potential. So let's say you go towards the right. The right is the direction of increasing potential, right? So the left regions over the left will be lower electric potential, right? So electric field will point towards the left, in opposite direction to the increase in potential. That's why there's a negative sign. You may be asked to explain this, okay? Right. And because of E equals to F over Q, right, your F will follow suit, okay? Now, when to use Coulomb's law, right, the inverse square law, Coulomb's law, use that you have a point charge. For the other ones, the other condition is parallel plate. You just use delta V over D. This one, you just have to follow dV dr, right? Okay, dV dr. Okay, let's look at MCQ, the first question. Okay. Right. Okay, a charge of 3 coulomb is stationary at point X in a uniform E field of strength 5 volts per meter. So this one will tell you that it's a parallel plate because it is a uniform electric field, right? Uniform electric field only applies to parallel plate. Okay, so you can't use Coulomb's inverse square law. It is then moved within the field 3 meters parallel to and 4 meters perpendicular to the field to point Y. Okay. Now, it's a positive charge, right? It's moving towards a region of a lower potential, right? So, what do you think the EPE will be? The EPE will actually decrease, right? Decrease. Once you move towards the lower potential, right, you must also see what is the charge. Not only looking at the E field, you must also see the sign of the charge. The charge is a positive charge. So if you move it along the E field line, right, the EPE should decrease. Okay, and what's the value? Now let's look at the answers. Okay, right, along the direction that is parallel to the E field, you will have a change in potential, but not in the direction perpendicular to the E field. Okay? So moving 4 meters perpendicular to the E field doesn't contribute to any change in the potential. So by moving horizontally, right, it doesn't cause any work to be done. Okay? Right? So you should use the formula W equals to Q delta V. Delta V will only be non-zero if you move along the electric field line. Okay? Parallel to the electric field line. So just use the formula Q equals delta V equals to E times delta D, right? Since it's a uniform E field, right, you can get an answer of 45 joules. And the change in EPE in this case will be positive or negative? What do you think? It will be negative. Okay? Because the charge will lose EPE by, the positive charge will lose EPE by moving to a lower potential. Right, because it will be repelled by the positive plate, right? So this loss in EPE will be causing the gain in KE of the charge, positive charge. So whenever you want to deal with whether there is an increase or decrease, you have to look at the charge. You have to look at the electric field direction. Okay, you have to look at the direction of motion of the charge as well. So 3 things to look for. Okay. Now let's look at the next one. If those of you don't have the printout, you can share, okay? Because this one is, I make it bigger so it's slightly truncated. This is another parallel plate question. What is the PD between point X and Y? So for this case, right, looks like your 15 millimeter is not important. You must consider because there's only a change in potential when you move parallel to the E field line. So it's actually between X and this point, see? Right, and this point, okay? Right. So if you use your electric field, you can use the parallel plate formula, right? Your electric field strength will be calculated to be 1000 volt per meter, right? Taking the potential difference between the 2 plates divided by the separation, right? And after that, you can calculate the potential difference between Y and X, right? It will be 20 volts. So answer is B, right? And which side do you think has the larger potential? Definitely will be the point that is closer to the positive plate. Okay. So X is the point with the lower potential. Right. So Y is the point with the higher potential. Right. Okay. Right. Okay. So the point below Y, vertically below Y, has the same potential as Y, right or not? Because you are moving perpendicular to the electric field direction, right? There's no change in potential. Okay. Okay, let's look at number 3. Now we are given the electric field strength, right? Then you must identify whether is it a parallel plate? Yes, right? So you cannot use the Coulomb's law or inverse square law, right? You must use E equals to delta V over D to calculate. Okay. Now, applying V, delta V over D, you find that the lower plate is actually of a higher potential, because they said that the electric field strength 3500 volts per meter is pointing upwards. So you have to know that electric field points from higher to lower potential. So the lower plate must be of a higher potential. So higher potential minus the lower potential, which is the upper plate, right, divided by D will give you the electric field. This will give you the potential of the upper plate being minus 18 volts. Okay. Right. This one is quite similar to next question. Question 4 is quite similar to the one that is inside your prelim. Remember, right? You are asked to find the subsequent motion of the electrical object, right? So it's quite similar, but they want you to find the magnitude of the viscous force, right? Now, in your prelim, you know the MCQ question you have, right? It's a straight line, but it's slanted. It's slanted, right? Why is it slanted, right? If you look at the free body diagram, okay, when it reaches terminal velocity, the viscous force which you can resolve in the horizontal direction must balance the electric force, okay, and the downward weight of the body, right, will be balanced by the vertical component of the viscous force upwards. Okay, so your viscous force will point in the direction that is opposing the motion of the straight line motion of the ball, which is slanted at an angle, right, which is the dotted, right, path in this case. Okay. Those of you who want to copy, right, I think you may choose not to copy, because I will send the answers to you after this session straight away. Okay. All right. So if you draw the vector diagram, if the object is having equilibrium, you can draw a closed polygon, right? And use Pythagoras theorem, you can get your magnitude of the drag force, which will be the same as the magnitude of the resultant of the electric force plus the weight. Okay. This one is slightly tougher because of the of the contour lines. Looks like a map. Can you just shift the 1 nanocoulomb, right, the dotted line, right, to be taken as this charge? Okay. So there are 3 charges there: 2 nanocoulomb, 1 nanocoulomb, and the other one, which is hidden here, is minus 2 nanocoulomb. The figure below shows equipotential lines. That means equipotential lines are lines of the same potential values. Okay. The E field lines, right? If you are told to draw the E field lines, it will always be perpendicular to a equipotential surface, right? So you can, from the equipotential lines, you can trace the E field lines, right? Okay. An increase in the electric potential energy of 4 microjoules occurs when the charge of magnitude minus 0.5 microcoulomb is moved from where to where. Now, here you have to take note that you must be careful to take note of the sign of the charge, which is minus 0.5 microcoulombs. Minus 0.5. If you want an increase in EPE, what must you do with the minus 0.5 charge? You have to move it to a lower potential or higher potential. In this case, it will be bring it to a lower potential. Okay, so you have to be careful, right? Because you have to do work against repulsion. No. Then there will be increase in the EPE, right? So you have to move it to a point whereby the potential is lower, right? Lower, okay. So this is directly opposed to that of a positive charge. For a positive charge, if you want to bring it to a point of higher, you want to increase its EPE, you must bring it to a point of higher potential instead. Okay, so we look at the answers. Okay. The change in EPE from an equipotential line to an adjacent line, adjacent means the next one of higher potential, right? You can use the formula delta U equal to Q delta V. Delta V is 2 volts because it's adjacent lines are 2 volts apart. This is given in the question. So delta U will work out to be 1. Oh, there's a mistake here. Right, 0.5 times 2, right, will give you 1. So it should be 1 microjoules. Okay, later I send the answers to you, you just cancel away, just put this as 1 microjoules numerically. Okay, 1 microjoules. An increase of 4 microjoules in moving the minus 0.5 charge must correspond to a displacement from one line to the fourth adjacent line, because you have 1 microjoules, right, when you move from one line to another, the next one. So you must move through 4 lines, okay, and you must move through a lower potential. So the best answer, you look at all the things, right, you count, then I think the best answer should be x to z, sorry, x to y is only 3 lines, so x to z, x to z. Yeah, z is not clear also, right? Z, in your question, can you put to like the point nearer to the dotted line? I mean the dotted, this diagram here, right? Let me show you. Because I think it shifted. Okay, z, z is actually this point. Okay, this equipotential line, Z. Z is lower potential because I know that because it is closer to the minus 2 nanocoulomb charge. Okay, so Z should be lower potential, right? Okay, so Z should be this point here, just shift the Z, the labeling Z up to this point, right? Okay. The regions just around Z, just around the minus 2 nanocoulomb will be the lower potential because it's negative charge there, right? So it should be lower potential, right? Yeah. Okay, let's move on. Oh, this is a very common question, especially I think this type will come out in your A levels, this type. You must be careful of the charges. It's sometimes very tricky. You're supposed to find the resultant electric field at the fourth corner, right? The fourth corner, it may contain a charge. If it contains a charge, you don't care about the charge at the fourth corner. So you have to add up vectorially, right? The most important thing is because it's an electric field, electric fields are vectors, you have to add vectorially. That's the most important thing. Okay. So do it separately. Now we can consider the 2 positive charges first, right? What is the field due to these 2 positive charges at the fourth corner? Then after that, you have to consider what is the field due to the negative Q at the fourth corner. Then you just add up vectorially. Okay, so we just look at the answers. Okay, supposing we let the length of the side of the square be d. So at the fourth corner, right, the electric field due to the positive charge Q, right, at the fourth corner will be this, this expression that you should use Coulomb's law because it's a point charge, right? And because electric field point from high to low potential, so it must be directed away from the positive charge. Right? So the electric field strength due to the two positive charges, right? You can use vectorial addition, right, to get this value, which points in the direction of C, right? So diagonally, right? Okay, away from the two charges. Okay. You need this one because you need to find the resultant to see whether the field strength due to these two positive Q is more or less than the field strength due to the minus Q. Okay. Now we consider the field strength due to the negative charge. Right. The negative charge is actually further away from the fourth corner, right? Because it's diagonally away from the fourth corner line. So the distance to the fourth corner from the negative charge is actually root 2 times d. Okay, root 2 times d. So the electric field strength due to that minus Q will be this value. So these two electric fields will point in opposite direction. One in the direction of A, one in the direction of C. Finally, your answer should be in direction of C because the electric field due to the two positive charges is actually larger, right? Right? You can compare the magnitude, so it's actually larger. Okay. Can I just understand? Don't need to copy because it's very wordy. So later I'll send the answers to you straight away after. Okay? Now look at this diagram. From this diagram, you can tell that the positive potential, higher potential, region of higher potential is actually at the left, right? The region of lower potential is actually to the right, because EPU points from high to low potential. But looking at the rod, right, the resultant charge on the rod right, is obviously 0 because Q minus Q, 0. So the charge of the rod times the E field will give you the force on the rod, right? So is there a force? Answer is no, because EQ, right, Q is 0, so force will be 0. So there's no resultant force on the rod. Okay, but is there a torque? Answer is yes. There's a couple. Okay. No, there will be a force acting right or left. Should be right, on positive Q. Right? It must be repelled away from the higher potential. So there will be a force horizontally to the right on positive Q at this point. Similarly, there will be a force, right, of the same magnitude of minus, towards the left. Right? So at these 2 points, right, it will give you a clockwise moment. Right? So there is a couple but no resultant force. It's a couple because the two forces are same in magnitude. Okay? Right? So answer is A. Oh. Okay, let's do at 8. An electron moves from X to Y under the influence of an electric field. The path taken is traced out on a diagram, marking out equipotential lines as shown below. If the electron speed is 3 × 10⁶ meter per second at X, what is the Ke at Y? So the electron has a negative charge. Be careful. Right? And it's going to move from X to Y. X to Y, if you look at the equipotential lines, signify that there is a increase in potential, right? So the EPE should increase or decrease of the electron. The EPE of the electron should decrease, right? Because it's moving towards the positive plate, right? Because 30 volts is more positive than 10 volts. Right. So the EPE should decrease, and the decrease in EPE should be converted to a gain in the kinetic energy. Correct or not? Okay? Right. So let's look at the answer. So there will be a loss in EPE because the electron moves from a position of lower potential to higher potential. So it's actually attracted towards the higher potential. So it will cause the Ke to increase and the EPE to decrease. Right. So if you consider this case, right, just use Ky. Ky is the kinetic energy at Y, the final Ke minus the Kx. Definitely you're going to give you a positive value because the Ke is increased, right? So if you look at the right hand side of the equation, right, the E and then you multiply by 30 minus 10, right? The electronic charge, you have to use the positive value 1.6 instead of minus 1.6, 10 to the power minus 19, right? Because you know that is the loss, right? You already know it, so you just put in the magnitudes, will do, okay? Okay. So your Ke should be larger at Y. So for this type of cases, you must know whether it's an increase in EPE or decrease in EPE before you can put in the so you can just take out the sign, right, when you calculate. Okay? Yeah, question 6. You all want to copy, Is there anything you want to copy? If not, I just go back. You need to copy? You want to copy, I'll just go back. If you don't want to copy, but it's too wordy, I'll send the answers to you, or you just come down later, look for me. Right. So let's go on to the structured one, which is quite long. Question 9 is okay, but question 10 is a little bit long. These are from the VJC past year exams. Okay, I think this one I purposely choose up because I think most of you all will make mistakes on this type of questions. What is the electric field at P? Right? You have to add vectorially. Yeah, a lot of students don't know how to add this vectorially because you can see from the common test. Right? So add vectorially, you have to consider the E field at P due to a single charge alone, just like just now the MCQ question, right? Oh. And here there's a right angle triangle, so it makes it easier for you, right, to determine the direction of the electric fields. Okay, so we calculate electric field. Right, due to Q2, E2 will be pointing radially outwards from Q2. So at P, E2 will have this direction, this one. Okay. Similarly, at what happened to the color? Oh, okay. So at P, E1 will be pointing radially away from Q1, because both are positive charges, right? And E2 and E1, you can draw a vector diagram like this, right? Then you add vectorially. Okay. After adding up vectorially, you can use Pythagoras theorem, because this one happens to be a 90 degrees angle, right? E2 and E1 is 90 degrees. Okay. So you can use Pythagoras theorem to add up. Then once you find the magnitude, don't just stop there, because you need to find the direction, because E field is a vector. You can use tangent theta, right? And then after you find 37 degrees, don't just stop there also. You need to say something. Where's the 37 degrees with respect to? Okay, it's actually with respect to the original E2 direction. Okay. The resultant potential, you just have to add up scalar addition. Okay. Right. Then you put in R. Both R's are 20 centimeters. So after working out, you will get this answer. Okay. Okay, finally, question. Yes? Oh, okay. Finally, question 10. Define the term electric field strength at a point. These are all very words, right? And the equation minus dV dr. Just now I told you, some of you are not here yet, right? The minus sign arises because of the electric field pointing in the opposite direction to the direction of increasing potential. That's why there's a negative sign. Okay. A student said there is no potential change in the region where the electric field is uniform. Comment on his statement. This type of comments are usually they are negative, right? They are not correct, So the statement is false. A uniform field is a field that is constant in magnitude and direction. So example will be in a parallel plate, right? But there will be a change in potential if you move along the field or anti-parallel to the field, or at a direction to the field, right? There will also, that means not at a direction but not 90 degrees to the field, there will be a change in potential, right? Okay, this one you clear? Okay, because we have used this one for question 1, 2, a lot of questions already, right? Question 1 and 2, right? Okay, so there will be a change in potential. If you move, if there is a component of the motion along or anti-parallel to the field. If you move perpendicularly, of course no. Okay. So let's calculate the electric force between the two protons in the nucleus. It's very big, right? See? 57.5 newtons. As compared to the weight of the protons, it's actually the weight of proton can throw away. It's negligibly small. Okay, right. Now even the two protons can be touching, right? If the two protons are touching, what's the separation between them? It's still not zero, leh. No. If the two protons are touching, then what's the separation between them? You can still count the center of the proton to the center of the other proton. Then the separation will still not be zero. Okay? Right. So the force is very big. But you can imagine this is the electrostatic force. The strong nuclear force is even much greater than this one. So it can bind the nucleus together. Right. Now to do work in moving the two protons together until this distance, right? That means you have to do it right from the start when the two protons are infinitively away from each other, right? Infinitively away from each other, right? So you have to do external work to bring it together, because the two protons will try and repel each other. So you have to overcome the repulsion and then bring it to this distance. Okay. So the work done against electric forces, which is provided by you, will be causing the increase in EPE of the two protons. Okay. So at infinity, right, your EPE should be zero. Right. Because R is infinite. So using Q1, Q2 over 4 pi E naught R, right, with R being infinite, right, the EPE at infinity should be zero, right? After, when you bring it to the distance of 2 femtometers, right, apart, the system will gain in EPE, right? Okay, so this is the amount of work that you need to do. Q1, you take the final EPE minus the initial EPE. Right. Okay, these parts are not related at all. Okay. And it can happen in A levels, whereby the questions are not related at all. Also, there's a possibility. So be careful. Look at part D, not related at all. Okay. You suspend a plastic ball, which is quite light, in the uniform electric field. How do you know uniform electric field? Because I see the two parallel plates up already. The left plate is 100 volts, right? The left plate is minus 100, the right plate is 100. So the right plate is at a higher potential, and the ball is being attracted towards the right. That means the ball must be negatively charged. Okay? And you have to calculate the charge on this ball. Okay? This one is not difficult. It's just forces. Okay, let the tension in the string be T. Vertically, T cosine 20 have to balance the weight of the plastic ball. Horizontally, T sine 20 have to balance the electric force on the ball. Okay. So electric force on the ball is E times Q. Electric field strength is V over D. Right? V, right, you must take the potential difference. That means it's 200 volts. Okay. Right. 100 minus 100. So the PD is 200 volts. This one I think students may also make mistakes. Right. Finally, you get the magnitude of the charge. Okay. It's minus charge, but you just take the you want a magnitude, right? The polarity has already been determined already, predetermined. Okay, the final one before we leave. Finish? Oh, wait. Another part which is totally unrelated. If a proton is released from rest in a uniform E field, how will its electric potential energy and Ke change? This is not too, let me see. Now, probably you'll get repelled by the positive potential and ends up being, right, the proton will go to a region of higher potential to higher potential higher EPE to a region of lower EPE, right? So its EPE will decrease and its Ke will increase. Okay, this is the most likely case. Let's check the answer whether it's correct. Right. So this decrease in EPE will be accompanied by an increase in Ke, right? And we should use this answer as the answer for the next one. Right. Part 2 is related, a little bit related. Okay. Right, because if you release it from rest in the E field, right, definitely you will gain Ke. But by conservation of energy, the Ke will come from something, right, which comes from the loss in EPE. Okay, let's look at the next one, which is the TV set. The TV set, this is the last time, I know, E part 2. Oh, you're supposed to calculate the change in EPE of the electron. So once the electron is released, this is an electron, okay, not a proton. It's released inside the TV set. It will be accelerated by a potential difference, right? So electron will move towards the higher potential. So it will be accelerated towards the higher potential. So in this case, right, the Ke gained by the electron comes from the loss in EPE of the electron. Right. So the loss in EPE becomes Q delta V. Okay. Q delta V. So there's a loss in EPE of the electron of this value, right? This is the old TV whereby you have using electric plates to accelerate the electrons, and then the electrons will then hit the fluorescent screen, causing the image to be formed. Oh, it's not your LCD, it's the old type of TV lah. Okay. whereby you have a very big thing at the back, right? Or to accelerate the electron, right? You have a very fat body at the back, right? Okay, so it's it's not very, it's wasting a lot of space, okay, and it consumes a lot of energy, right? Also, then you have to know the potential difference of the accelerating PD is about the it's about the region of 1000 volts, okay. Now, what is the final speed of the electron? Assuming it starts from rest, right? The gain in KE will be the loss in EPE lah. And you can find the speed, okay? This type of question, remember to use the correct mass. Right? Many of you use the wrong mass. Sometimes some of you will use the mass of the proton, right? Because you're out of time already, then you may do sorts of careless mistakes, right? Okay. Yeah. Okay. Other than that, we will end here, right? And I'll send answers to you right now.